Hi everyone. It's my first presence at a TUG meeting, so I'm probably in equal parts excited to be here, humbled and slightly intimidated also to present in front of all of you, especially those of you whose software I've been using for many years now. So I guess I would like first to acknowledge my thanks to all of you who've been doing all this work. So I can see now why I was scheduled immediately after Mitch, since it will be a second talk in a row on literate programming, only from a quite different perspective. I mean, thanks to Mitch for his historical perspective on it, although I'll touch it slightly. Actually, my talk is more of a sort of a trick. I think it is clever, but maybe it's just obvious for some of you, so I really don't know. But it's proven pretty useful for me for quite a number of years now. So that's what I'd like to present this morning. I'm a professor of actuarial science at Université Laval, that's in Quebec City, Canada. It will play a role in the sense that the examples that I will present are in a context of a teacher that is preparing material for his students. Okay, so it may not apply to you, but perhaps you can transfer the idea if it can be any useful to you. So the title of the talk is actually a wordplay on the famous poem by Jean de La Fontaine, the caterpillar and the ant. But it really stops there. I mean, it's just a wordplay. It has no other meaning hidden in there. That what is the caterpillar? What is the ant? Is it weaving, tangling, whatever? It's just the wordplay. If we take the French version or a word-to-word translation, it's much closer to the title of the talk than the version that I put there. That seems to be sort of the sanctioned translation on the web. The software tools that have had the biggest impact on my work over the last, say, 25 years or so are the following. First is the R programming language. So I'm more of actual science is closer to statistics than anything else. And when I started working with R, that's quite a number of years ago. I'm proud to say that I started using R when the version number still started with a 0. It was the first language that I was using that had embedded statistical procedures in the language. Before that, I was programming in APL, where you had to program the mean function by yourself. Second, eventually I ended up using version control. Again, might be quite obvious for many of you, especially the gentleman there who has the t-shirt with a Git joke. And eventually I also learned about literate programming when the Sweave system to do literate programming with R appeared. And I so much like these tools that I actually teach it to my students, each and every one of them, because I find them important. So we teach R as the first programming language to our students in actual science, and within that course I teach them immediately to start using programming using Git, and eventually we come to literate programming, especially using R Markdown. So yeah. So of course, literate programming, as Mitch mentioned, was pioneered by Donald Knuth. This is the quite famous quote from the start of his article. Mitch mentioned 1984, I think it's 1982, but he may be better than me on historic things. Yeah. I won't go into much more details on this since we had a very interesting talk on the subject already just before that. So let's set the stage for my presentation of my little trick. So the players are, well, first if we look at literate programming in a nutshell, so the idea, as mentioned, is to combine documentation and a program in one single file, and to create either the documentation or extract the code. I wrote here extract the documentation. It's really create the documentation, because usually a part of the documentation can be created from the code itself. So the weave procedure is there to create the documentation, and we have a tangle procedure to extract the source code. Now, for many years, I was wondering, I was thinking that weave and tangle should be opposite terms of one another, and I couldn't wrap my head around, well, just by reading the translation. I'm French speaking, so I was trying to understand. I mean, these two words seem to mean essentially the same thing, weaving, tangling. They're very, very close, and certainly not opposites. And it's just a couple of weeks ago when I actually read the Knuth paper that I discovered why he called that procedure tangling. It's just that the source code that was created by his web system was all tangled together, and it was not that much readable, the tangle code. So that's why he called it tangle. So it's not at all the opposite of weaving. So there were many literate programming systems that were developed over the years. Of course, the original web system by Knuth, is a C implementation a few years later. This system, web, was quite more evolved in a certain way than the systems that followed, because the web system used it was not just documentation and code, but the way the code was written was interpreted by the system, something that we don't necessarily see in the other systems that followed. Of course, we have the doc system that is still very much in use to write documentation for packages and classes. No web, that will play an important role in the sequel. I'm just naming a few ones, of course. If you invented one and you're not cited here, don't be mad at me. The Sweave system that was important to me, introduced the idea of literate programming with R. And eventually it moved into knitr, which is another system that I know Boris is familiar with. So here's a short illustration of what a literate programming system would do. Is basically, so we start with a file. Here I made a depiction with a system that is using LaTeX as the language for the documentation and R as the programming language. You can adapt this to any other combination of markup language and programming, and it's not really important in the sequel. So we have one file that contains the documentation and the programming code, and we can extract or create the documentation itself using a weave procedure that will turn here in this example our document that will what the weave procedure will do is that it will look at the code, probably execute or evaluate part of the code, and replace the code by actual documentation or material that will be suitable LaTeX code, turn this into a text document, and then that you can compile, of course, to, say, a PDF file. Or the tangle procedure, usually, I think in most systems today, will essentially just extract all the code chunks that you will have in your original file and throw the documentation away and just retain the programming code. Here, that would be our code in my example. So nowadays, literate programming plays quite an important role in science and data science in particular. I mean, literate programming is now considered a cornerstone of what we call reproducible research. So so the idea is you tell people, well, don't key in the results of your paper in the paper, generate the results from the code immediately to the paper. So you'll avoid mistakes. If you make changes to the code, the paper will always be in sync with the actual code. So it's quite an important topic now. And it's also an important concept between the leading tools of data science. Here I'm thinking especially about what many companies call notebooks. A Jupyter notebook is just a literate programming system. We have the same thing for R Markdown and many other systems that rely on the concept of literate programming. So it's still quite an important tool. But in these tools, usually the emphasis is really put on the weave procedure. The idea is that we want to write documentation, intersperse it with code, and eventually create some more documentation from the code. But quite, not so often do we hear about the tangle procedure. So the idea here is that eventually, when I started doing literate programming and using it, I found it very, very useful to use the standard path of basically writing a document in LaTeX. If I need to write an example of running some code, that I will just put the code in the file, run it through Weave, and generate the answer or the documentation material straight from the code, and do it like that, or generate graphics from the code and so on and so forth. So for many years it was just a very convenient use case of the system. But eventually I had some slightly different needs. For example, I need to maintain documentation and code together, but they're sort of independent in a way, in the sense that I don't need the code to generate the documentation. Okay, so the documentation can hold all on itself, but I have code. Of course, they're related, but the code is not used to generate the documentation. So there's no real need for literate programming there. But eventually, I could need to include the code inside the document. So just to typeset it inside the document, the code is not used to create a documentation, but I want to use it to show it inside the documentation. You'll see an example in a moment by what I mean there. So I was not exactly in the literate programming scenario. Also, I could have code chunks that will be evaluated in the standard weave procedure that would rely on some other part of the code, but that is saved as files on the hard disk. So I don't just want to reuse a code chunk that is somewhere else in the document, but the code chunk must be saved on as a file before. But I want to maintain everything together, but it has to be in a separate file, but I want everything to be in the same file. So I had to find some other way to do this. And I wanted a self-contained solution, something that would be done in just one step. And self-contained meaning that I try to remain only inside the system of weaving and tangling. Of course, you could say, well, just do it using some external tool like Make. Of course, you can do everything you want and plan all these things using Make. I was trying to do it without using an external tool like Make. Okay, so here are a couple of examples. So I'm still not showing the trick. I'm still just showing you what I was trying to achieve. So I have one document, one textbook that I wrote for my students on programming with R. And so basically I have the text of the manual, of course. I have sample R code that is included at the end of every chapter. Okay? Of course, it is distributed separately as just script files, but I wanted the document itself, the PDF document, to also contain the R code. So this sample code is included in the manual, but it's not otherwise used to create the manual itself. It's just sample code. So originally, what I would do is to maintain all the files separately. So I would have the text files that would contain the text of the manual, and I would have the sample code separately in .r files. So it proved a little bit, it worked perfectly well, but it proved a little bit cumbersome to synchronize the two documents. If I would make a change in the manual, I would need to remember to open the R file and do the adjustments there also. And first and foremost, I would obviously compile the document and check, well, okay, everything is correct in the document, but I would not so often think of checking whether my R code was correct by just evaluating it. So, and actually there were tons of mistakes in these R files because I would just not think of checking them. And remember, I said, no, you cannot argue, well, you should have done it with make and make sure that everything is always checked. I was just not using it. So eventually I came up with a system where I can maintain everything in .rnw files, so literate programming files. So many files because I have one file per chapter, okay? But every file for one chapter contains the code for the documentation and the sample code also. So I have obviously fewer files to maintain, but what I eventually could come up with is the fact that I could split the sample code by section. Instead of having one large file of sample code, I could just write if there was sample code for one section of a chapter, I could just put the sample code for this section after the section, start writing another section, then the sample code, and so on and so forth, instead of maintaining the sample code in one large file. And what this system provided me with is the fact that each and every time that I compile the document, the source code is actually evaluated and checked. So if there's a mistake in the sample code, the compilation will stop. Okay? One caveat there was that these files of sample code that are included inside the typeset document need to exist, because somewhere in my tech code I have an include listing something to include these files to appear in the document. So I needed to have the files present on the disk to be included back in the document. So basically we need to extract the material from the source, create the sample code, and then include back these files inside the typeset document. Here's one other example, slightly more complicated or involved. I have a term project that I'm distributing to my students and a lot of material to maintain. So obviously the text of the assignment itself, okay? So that's the documentation part. But I have a lot of other material to maintain. The solutions to the term project that I want to give to my TAs or to myself. I distribute unit tests to the students so that they can test their own functions on tests that I design myself, so that they can check whether their functions are correct. So I give some unit tests to the students, but I have other tests that are used for grading purposes that I need to give to my TAs. Also, to do the grading, we need some shell scripts. And on top of that, we have some configuration files, just very, very simple text files that are used for a grading system that I designed. So a lot of material that I have to maintain. Originally, it would all be in separate files, perhaps in one subdirectory of the directory for my course. With the system that I've been using for a number of years now, I can maintain everything in one single file. I say huge file. I mean, let's just tone down the scale here. The file is not that huge, but it's huge in comparison to the number, to the length of the material to create the actual document that the students see. Actually, I have about 900 lines, so about 6 or 7 pages for the material that is distributed to the students, but I have 3 times as more lines of code for everything else. That's all in one file. So I have a very close proximity between the questions that I ask to the students and the solutions, because in my document I can write, well, do this type of function that will do this and that, and write the solution immediately underneath it. Obviously, the students don't see the solution. But I can maintain everything in very, very close proximity instead of keeping that in separate files. It's much better this way. It's much easier to maintain. And one other very, very nice thing is that the unit tests that I give to the students, that I give to the graders, they're all executed also when I compile the document. So in other words, I'm sort of auto-validating my own code each and every time. The only thing I have to be careful about is to write a question that matches the solution. Because the solution, it works, it passes all the unit tests. So the really crucial point here is to ask the correct question, basically. Okay? So each and every time that I compile the document, I'm quite confident that I have material that is consistent, that it works together. Again, the unit test, in the unit test, we have to import the solutions. Okay, all the unit tests work this way, by reading in the code, so the files have to exist again on the disk before we can run the unit tests. So the unit tests cannot rely on a code chunk that is somewhere in the document, because the unit tests are written in a way that they should read an external file. So what's the trick? Well, we have a weave procedure that in the R terminology is called Sweave. Why not R weave? Because it was designed at a time that R was still seen as the GNU version of the S system. But the S system no longer exists, actually. It's one of a very, very rare case of an open source software that virtually killed the commercial counterpart. So, they used S as a prefix for historical reasons. So we have a Sweave procedure that evaluates all the code in a .rnw file. And we have tangle, or the tangle procedure, that extracts all the code from a .rnw file. And I need to do both, actually. I need to Sweave and tangle in the correct order. So the trick, basically, is just to combine the two by using the tangle procedure inside the weave procedure. So when I weave the document, I first tangle it. So that I can create the source files on the disk and then reuse them after a while. So that's the trick, basically. Remember this diagram that I showed earlier? So where we had sort of very separate paths between weave and tangle. Well, what I basically do with my little trick is to go this way. through the diagram, is to always start by weaving, but at the beginning of the weaving procedure, we first tangle, finish the tangling step. Once tangling is done, we complete the weaving step, and then we end up with the PDF document at the end. Here's an example of how it works. So, very simple document. Here, the notation is that we have these symbols to activate a code chunk. This is no web syntax, and the @ returns to documentation mode. And if we don't put an equal sign after the brackets, it just means include another code chunk. Inside a code chunk, you can use a code chunk that was defined previously. We'll see that on the next slide. So here's the idea here. The very first code chunk is in my document, actually calls the tangle procedure. So the first thing that gets source name is just a way an internal function that I wrote to sort of retrieve the name of the file that we're actually compiling. This, we'll come back to this in a moment. But you see that the first step, the first code chunk that is evaluated in the document is actually to start tangling the document first. So here we have another section. This is just a regular weaving procedure where we can define, this is a solution basically, where I define the code of the solution, and since the code chunk is named, it will create on the tangle step, it will create a file called importstations.r. So at the tangling step, the file will be created. On the weaving step, the code will be evaluated, and a function will be available for the following code chunks. So that, for example, later in the document, I can use the function and show usage of the function. This will be created by the weave procedure naturally, just like the usual way we use literate programming in data science. Now, if we look at the unit tests now, let's just assume that I mentioned in the previous slide that a file called importstation.r would be created. Let's just imagine here or assume that another file called revenues.r will be created also on tangling. So now tangling is done. My files are created on the disk, and weaving of the document continues. And eventually we end up on the following code chunks. Well, these code chunks, what are they doing? They're the unit tests that on tangling will be created as .r files that will be distributed to students. But now we are weaving the document. So the code is executed, and these unit tests, what they do is they import, they have to source the R files. These files now exist because they've been tangled before. So we can reread the file, execute all our unit tests on the weave procedure because I tangled first. And then I'm weaving, and now I can rely on the material that's been tangled. And here, just for the sake of it, just to show a little example of what we can do, is that these code chunks, they're actually not tangled because I don't want to have separate files for each and every test. I want one big file for all the unit tests. So basically what I distribute to students is one large file containing all the unit tests. So how is this file created? Well, by just creating one large file at the end, one last code chunk, that will import all the other code chunks and create one large file. This these code chunks will be evaluated at the weave procedure, but not the later one, because we don't want to execute the unit test twice. We just want to evaluate them once. So here actually, so this is basically how I can manage to maintain all the material in one large file. I think it's, if not clever, certainly useful as a way to maintain documentation and the rest of the code. Here, ignore on tangle, ignore on tangle, and ignore on weave are not standard keywords that are supported by Sweave. So I might just say a couple of words on just a small R package. I mean, maybe very few, if none of you are actually working with R, so I'll be very, very short on that. But the idea here is that I just wrote a very small R package that provides additional Sweave drivers with, as I wrote here, extra tricks up their sleeve. So the idea is that when we say ignore on weave, it means that when we are weaving a document, we can just completely skip the code chunk. So what it allows me to do is to maintain code inside a Sweave document that is in other languages than R, that would otherwise not be, that it would not work on the, or that would stop the weave procedure otherwise. Ignore on tangle can ignore a code chunk on tangling, yet weave it as is. So it's just a way to avoid cluttering on the file system to create, otherwise tangling will create one file per code chunk. And there are some code chunks that I know I don't want to be saved as files, so I can just say, well, ignore this one, don't tangle it, I don't need it. And eventually I added another option that's called the extension. So when I have code chunks that are in other languages than R, tangling will always extract them to file with a .r extension. And sometimes it's just text file, for example, because I maintain the README file inside my big document. So I could just extract it to .txt or .md, whatever, by using an extension trick there. So yeah, I guess that's it. I hope it will be useful. These and I don't know if you spotted the movie references there written there. So thanks very much for listening.
Probably expected this question. Did you try to port this package to knitr as well, your R Sweave extra, to make something like R knitr extra package?
To port it to knitr?
To knitr package.
Yeah. So for the record, knitr is another system built after Sweave. Originally, knitr was a system that added a lot of options to Sweave. Personally, I always thought it was just too much. Well, Sweave was lean and mean, and I always stuck to that system. Eventually, knitr became the basis for R Markdown, which is another literate programming system where the base is not LaTeX text or LaTeX markup, but instead Markdown markup. That's what I teach to students because it's easier for them. But I also tell them, and I'll come to your question in a moment, I also tell them, well, our Markdown or Markdown in general, it's very, very good to do simple things. But it's very complicated to do complicated things. I mean, simple software are useful to do simple things. And especially for students who need to write mathematics, quite often they eventually need to know LaTeX. So I usually tell them, well, just learn LaTeX in the first place and you'll be done with it. I'm not a user of Markdown. I always stayed on the LaTeX side and Sweave, so I did not really look into porting it or doing it, making it compatible with knitr.
Any more questions before we go to coffee? Yes, Nelson.
One of my many activities is maintaining Unix.bib, which records articles about Unix and its history. And one of the things we've tried to do on the Unix Heritage Society mailing list is dredge up copies of a lot of old documents. And as you observe, and also the previous speaker, sometimes these have disappeared completely. Mm-hmm. And I raised the question a couple of months ago about the sources for the S language, the original statistics language from Bell Labs, and got only a couple of responses. And then someone said, well, you know, John Chambers, the architect of S, is still alive and working at Stanford. Why don't you ask him? So I did. And he confirmed, as far as he knows, those sources are gone forever. Wow. They're documented in a book, but nobody seems to have copies anywhere. It's possible it will still turn up somewhere on some tape that somebody uncovers. One list member reported that he recalls building it from source code, and it was a mass of Fortran and C, and quite complicated to deal with. But it is well documented in the original blue book that Chambers wrote with another author. But unfortunately, there are a fair number of instances in computer science, or probably the youngest scientific field, where the original materials are gone, and we can't get them back, and it's very, very sad. It should never have happened.
Yeah.